So welcome back. This is our third video about belief propagation, and now we're going to talk about the join graphs. So a join graph is basically a join tree with some relaxations. So we can remember from the previous lecture, the previous video that we were discussing, that we can use the idea of belief propagation to create a whole family of methods. So this family of methods will go through very simple methods that can be very efficient but highly approximated, to methods that are exact but can have a much larger computational cost. So we saw two examples of those methods. In one side of the spectrum, we have the belief propagation algorithm that uses a join tree based on a polytree to make inference. And on the other side of the spectrum, we have the join tree algorithm that we saw a few lectures ago. So this join tree may have larger clusters and separators, so the cost of making inference using the join tree is going to be larger, but it is guaranteed to provide the correct marginals for the variables that we have in the network. So now we're going to use another idea, that is, we can modify the join tree to reduce the size of the separators and the clusters, creating a new structure that we're going to call the join graph. And as the name suggests, the difference between the join graph and the join tree is that the join graph is a graph and it accepts loops. And we know that when we have loop in the structure that we're going to make inference, we will have that problem that we need to send some initial messages with predefined values and going to iterate over time in order to get an approximation. So the join graph will be very similar to the iterative belief propagation algorithm that we discussed in this lecture. So in order to not create any confusion, we're going to make a differentiation between the iterative belief propagation that we saw before. It is one approximated inference algorithm that assumes that the underlying structure is a join tree, and the iterative join graph propagation algorithm that we're going to discuss in this video that assumes that the underlying structure is a join graph. So let's start defining what is a join graph. So I'm going to see that's very similar to the join tree, but now we're going to allow loops in the structure. So it says here a join graph G for a network N is a graph. So it's not a tree anymore, where the nodes are labeled by cluster Ci and the edges Ij are labeled by separators Sij. Moreover, G satisfies the following properties. The first one is that the cluster Ci's and separators Sij are set of nodes in the network. Okay, that is very similar to what we had before for the join trees. Each factor in the network must appear in some cluster Ci. That's also very similar to what we had before for the join trees. And now the differences. They have two here. First, if a variable x appears in two clusters Ci and Cj, then there exists a unique path connecting I and j in the join graph such that x appears in every cluster and separator on the path. Okay, so we have one example of Bayesian network here and the join graph here. We can look, for instance, for variable a, and a is appearing here, here, and here. But it's important that there is only one path that connects these two clusters, this cluster and this cluster. There is this path here, right? We cannot have a here. If we had, there would be two paths, two different ways to come from this guy to this guy here, and that will be would lead to an invalid join graph. And the last property here says that for every edge Ij in the join graph, the separator is now a subset of the intersection between the two clusters. Before, when we had the join tree, we were obligated to have the separators equal to the intersection between the two clusters. And now it's just a subset, right? So it's happening here as well with a variable a. We can see that in this case, we have a and b in this cluster and a and b in this cluster, but now we define that the separator as just b and not a and b, right? And it was important in order to not create two paths connecting these two nodes. So we can see the join graph as a sort of a relaxed joint tree. So for instance, these are two examples of one joint tree and one joint graph for the same Bayesian network. And we can see here that we made a small change and we could reduce the size of this cluster here. Right? In this case, now the inference is going to be slightly more efficient because we reduced the width of the joint tree by creating a joint graph. On the other side, we will see that the inference will not be exact. It's going to be an approximated inference with approximated results. But in terms of definitions, what we can see, when we have the joint tree and we have two nodes with the same variable, we have the obligation to have the variable appearing in every separator and every node in the path, right? And there was a single path because it's a tree, right? So in this case, I have C here and I have C here. I am obligated to have the C here, the C here, and the C here as well. So C, the variable C is appearing in every separator and in every cluster in the path. But now, with the joint graphs, we can have multiple paths between two nodes. And in this case, we say that just one path can have the variable and in the clusters and separators. So in this case here, if we look at the variable C and the variable C, we're going to see that C is appearing in just one path because there is one path over here and there's another path over there. So, but C is appearing in just one path connecting these two nodes. If I include C here and include C here and C here as well, in this case, I would have an invalid joint graph because there would be more than one path with the same variable. Another difference is that now we do not require the separators to be the intersection between the nodes, but they can be a subset of the nodes. So as we discussed in the previous slide, it was the case here with these two nodes that we have on top. These two guys here, they mention variables A and B, but only B is part of the separator. So it's a subset, but if we had a joint tree, we would be obligated to have A and B in the separator. Okay, so let's use one example to check our understanding. So the question here is if this joint graph is a valid joint graph or not for this set of factors. So suppose that we have a Bayesian network or a Markov network that has those factors here, and we want to know if it's valid or not. So there are four properties that we discussed. The first two are very similar to the joint tree. So it says that the clusters and separators are set of nodes from the network. So it says that it is correct because what we see in the joint graph are mentioning variables A, B, C, D, E, and F. So these are the variables occurring in the factors. And each factor must appear in some cluster Ci. So we needed to have the joint graph with clusters that are large enough to receive all the factors that we have. So we cannot have a factor that cannot be associated with any clusters because the clusters do not mention the variables in the factor. So we can double check that. So like we could put this guy ABC here, this BC, we can put it here, or you could put it here as well. So we have an option. We cannot put in both clusters, right? Just one or the other. BD, we can put it here. We have DE, we can put it here. We have BE, we can put it here. We have BD again, we can put it over there. And we have BDF that can only go here. So, okay, we have a space for everyone, so we are fine. The next test that we needed to do is to check if we have the unique path between two nodes that mention the same variable. And there are two things here that we need to check. First, there must be a path that connects two nodes that mention the same variable. And this path must be unique, right? So there is the existence and the uniqueness, and we needed these two properties. So when we look here and we see the variable b, we can see that b is mentioned here, is mentioned here, is mentioned here, and here. So that's fine, but b is also mentioned here, and there is no connection between this node and this node mentioning b, or the other nodes that we have there mentioning b. So there is no b over here, there is no b over here or over here. So what we have is a separated cluster that mentions b but has no communication with the remaining of the graph, and that is bad. We cannot allow that. So we can imagine why, right? So if we have the messages, no messages will mention b when we exchange over these separators here. So this here will be over c, and these here will be over d. So they are not mentioning b. So what's going to happen is that here we have a sort of an island mentioning b, disconnected with everything else that has information about b. So we're going to create here one marginal mentioning b that is completely disconnected with the other marginals that mention b. So this here, if we compute the probability of b by looking at this cluster here, it can be very different from the probability of b that it can achieve by looking at the other clusters, and that is very bad. So we need to have a communication between these two sides. So that is important to have this path. So this is the existence property. We must have the path connecting the nodes, the clusters that mention the variable. All right, let's take a look at another example. So this is another example, but now we included b in the separator here, right? So we have b in the separator here, and we have b in the separator here. So now we have another problem that instead of having just one path connecting, for instance, this cluster here that mentions b and this cluster that mentions b, we have two paths, and that is a problem as well. And we can see that by imagine what will happen when we send the message. So imagine that this cluster here sends a message mentioning b to this cluster, and this cluster sends a message that mentions b to this cluster, and this cluster here, you're going to send a message mentioning b to this cluster back here. So you should remember that, and we mentioned that several times when we discussing message passing, that when I send a message to you, we do not involve the message that you send it to me, because we wanted to avoid what we call the self-assuring beliefs, the self-assuring messages. So for instance, if you send me a message saying what you think about the probability of b, and I repeat that information back to you, so you'll be more confident that the probability of b is that value, and we're going to send this back to me and repeat it to you, and we keep in that loop. So this is a bad thing. In this case here, it is going to occur because we have this cluster. Let's just me erase here. So we have this cluster here, for instance, telling this cluster what he thinks about b to this cluster, and this cluster will incorporate that information when it sends the message about b to this cluster, and this guy will take this information that actually was from the cluster 4 in some way back to cluster 4. So it will make in a slightly more indirected way a self-assuring information about what cluster 4 thinks about the variable b. So this is a bad thing. So we need to ensure that there will be no loops, because when we have loops, the tendency is to create very extreme values for the probabilities, because the clusters, they hear back what they said and they start to change the values, so we have to inflate the values of the probabilities that we have. So this is one example of a valid join graph, and a simple way to check that is to look if the variables in the nodes and separators, if they form a tree. If they form a tree, you are fine, right? So what I mean by that is that, for instance, we take the variable a and look at the variable a here and see in which other clusters and separators a is occurring. So in this case, a is just occurring in this cluster, so we are fine. We can go to B and look at B and see that B is here, here, and here, and also this here. It's going to be a tree, so we are fine. It cannot be a forest, so it cannot be a disconnected tree, but we can also accept the loops, right? So we see that it's correct for B. For C, can just erase it just and look at the variables of C and see where C is occurring. So C is occurring here and here and here. So again, we have a tree with just these three, two clusters and the separator. D, in the case of D, we have a D here, D here, D here, here, and here, and that's all, right? Again, we have a sort of a tree, so we have no loops, we are fine with that. We can look for E. Here is happening in these two clusters and separator, so we are fine. And finally, F is happening here and only here, so it's fine. So we have a valid join graph. Okay, and we can understand the join graph as a probabilistic graphical model, so it will induce a factorization that is in the same form that we have discussed before. Is a multiplication of the clusters divided by the multiplication of the separators. The difference now is that we're going to have different clusters and different separators from the joint tree. In the case that the joint graph is a tree, there's going to be a joint tree, and the factorization will be exact. Otherwise, we will have an approximate factorization, and the results that we get for our computations will be also approximations. So there is one special join graph that we call the dual join graph, and this join graph, it produces the factorization that is used by the iterative belief propagation algorithm when we do inference over a network that is not a polytree, right? So for instance, here we have a network that's not a polytree, and this is the dual join graph that is created by this polytree. So basically it's the same idea of the joint tree that we created for the polytrees. We have nodes, one node in the dual join graph for each node that we have in the Bayesian network. We also have one edge for each edge, and the nodes are defined according to the variable. So here we have A and its parents, but A has no parents. B and its parents, it's just B. Here we have C and its parents at A and B, and here we have D and its parents A and B, and finally here we have E and its parents that are C and D. And the separators are over single variables, right? Exactly as we had before. And the separators are the parents of the edges. So here we have an edge between A and C. The parent is A, so here's going to be A. Here we have B as a parent, A again and B again. And here we have C and D, so we have the separators are C and D. Right? So very similar to what we described before, but now in the form of a join graph. So in this slide we have the Bayesian network, we have the dual join graph, and we have also the factorization that is induced by the dual join graph. And we can see that we are conditioning to E. So every cluster and separator is conditioning to E. That is in the case that we have evidence, but we can also drop this if you want to and compute, use this factorization to compute results to a query that do not involve evidence. So we see that we have the probability over the clusters A, B, ABC, ABD, and CDE, right? Exactly as we defined it here, and divided by the probability of the separators A, B, C, and D. So we have A 2 times and B 2 times, so we are here square it and square it, and C and D just once. And we can look at this factorization and compare with the chain rule for this Bayesian network to see what are the differences in terms of independence assumptions. So I will drop this conditioning to E in order to make it a little bit easier to write. So we have the following expression. So we have the probability of A, I will keep it, we have the probability of B. Let's keep, and because this is occurring in the Bayesian network, we have the probability of A, B, C, and we're going to write this as the probability of C given A and B. And in this case, we need to multiply by the probability of AB. We have the probability of A, B, D, but what we need is the probability of D given A and B times the probability of A and B. And we have the probability of CDE, but what we care about is the probability of E given C and D, and I'm going to multiply with the probability of CD. And that's going to be divided by, we have the probability of A 2 times, and we have the probability of B 2 times, and have the probability of C and the probability of D. All right, so this one checks with the Bayesian network. This is also checked with the Bayesian network, as well as this one and this one. So what we have to explain is this guy here, this guy here, and this guy here, and also everyone that is in the denominator. What we know is that for this Bayesian network, it's true that A is independent of B. And if we assume this, so in this case, we can cancel this guy with these guys and cancel these guys with these two guys here. But we still need to explain this guy here. And basically what it's saying is that to eliminate these 3 terms, we need to assume that C is independent of D. And that is not true, right? So we see here C and D, they are not independent. In order to make them independent, we need to observe A and B. So the correct independence assumption is that C is independent of D given A and B. So this should not be the correct distribution for our problem, but we can still use it to approximate answers for our queries. Okay, now we have another example here, that is the joint tree. And this is the joint tree for this Bayesian network, so it will allow exact inference, right? So it will not be approximated inference. So let's take a look in the factorization and see if the factorization corresponds to the factorization that we can find in the Bayesian network, or if it's assuming anything that is incorrect. So I will again drop this conditionally to evidence in order to make it a little easier to write. So we have the probability of ABC, but what I want is the probability of C given AB. So I will multiply this by probability of AB. And I have the probability of ABD, but what I want is the probability of D given AB. So I will multiply the probability of AB. We have this probability of A, B, C, and D. Let's keep that probability of A, B, C, and D. And we have the probability of CDE, but I want the probability of E given CD times the probability of CD. Okay, and now that's going to be divided by the separators, that they are probability of A, B, C, the probability of A, B, D, and the probability of CD. So we can cancel this with this, and we can check what we have, right? So we have this guy here that corresponds to this one. This one we have to see what we're going to do with that. Probability of D given AB. We have this guy here, check with this. Again, we have to check this, but we have this one that corresponds to this one here. So we still have to find factors for the nodes A and B that we can take from this joint probability of A and B together. Okay, the next step that we can do is to assume that A is independent of B. So I don't have much space here, so I'm gonna write just the terms that we still need to explain. So I will convert this guy here as the probability of A and times probability of B by assuming that A is independent of B. That's actually true for this network here. And we have this term we have explained it. We have this probability of A and B that I can write also as probability of A times probability of B. I will transform this term here in a way that I can cancel with one of these two terms that I have at the bottom here. So I can write this as the probability of, I want ABD, so going to be the probability of C given ABD times the probability of ABD. So I can cancel ABD. So I can cancel, and I have already explained the other terms, and this guy here, I will cancel. So I have the probability of ABC, and I have the probability of AB. So I'm going to write it like this: the probability of C given A and B times the probability of A and B, and the probability of ABD. Okay, so I can cancel this with this. I can cancel this with this. If we assume that A is independent of B, as we assume, we can also say that this guy here is A, probability of A times probability of B, as well as this one, that we can cancel all the terms. But now, what we have, so this is the P of A and P of B. So check with these two guys here. So what we haven't explained yet is these two terms. So in order to cancel them, we have to assume that probability of C given ABD is equal to the probability of C given AB. And that's going to be true in the case that C is independent of D given A and B. And actually that is true by this network here. If we look, C is independent of D if we observe A and B. That's true. And okay, that's one assumption that we have. So if we look at that, we can explain all the terms that we have in the factorization. They will correspond to terms in the Bayes networks, and the terms that we could not explain, we can eliminate them by assuming independence assumptions that are present in the Bayes network. So we are fine. We are not assuming anything that is not present there. So finally, we have the joint graph that will trade complexity by quality, and we can see that we had in the joint tree 4 variables in this node, and now we have just 3. So it's going to be slightly more efficient, but it will be an approximate result. So we can take a look at how this joint graph corresponds to the factorization of the Bayes network, but I'm going to do in the next slide because I don't have much space here. So, okay, we have this. Just checking what we have. They have the probability of ABC, one cluster, another cluster here, ACD, another cluster, and CDE, another cluster, divided by the probability of the separators B, AC, AD, and CD. Okay, it's correct, exactly as we expected. So let's see if we can turn these into factors that correspond to the factorization that we get from the Bayes network. So we have this probability of ABC, but what I want is the probability of C given AB. So I can write like this: C given A and B. We have ABD, but what we want is the probability of, so times AB, sorry. We have a probability of ABD, but what we want is probability of D given A and B times probability of AB. We have a probability of ACD, yeah, let's keep this probability of ACD. And we have probability of CDE, but what I want is the probability of E given C and D times the probability of C and D. And I'm going to divide this by the probability of separators, probability of B, probability of AC, probability of AD, and probability of CD. So we can cancel this, we can cancel this. There is nothing else that we can cancel, but we can eliminate some terms that we can explain with the factorization of the Bayes network, like we have here CAB, going to be this factor, D AB going to be this factor, and ECD here going to be this factor here. So the terms that we still need to explain are the following. I'm going to write these down here. Probability of A and B that will split with independence assumptions between A and B, and this probability of ACD. And what we have in the denominator is probability of B, the probability of AC, and the probability of AD. Okay, so what we can do now is assume that A, B are independent of each other. So probability of A, probability of B. Again, probability of A, probability of B. And we have the probability of ACD. I won't cancel with something that I have in the denominator, so you write this as a probability of C given AD. C given AD times the probability of AD. Right, so I have this, and we have this in the denominator. Probability of B, probability of AC, and probability of AD. And we can cancel this, we can cancel and cancel. We still need to explain. So this is A and B, so let's check. So we still have the probability of A and the probability of C given AD. That still need to be explained, and I'm going to rewrite in the denominator as the probability of C given A times the probability of A, so we can cancel this and this. So now we have this condition here. We have the probability of C given AD equal to the probability of C given A, and that's going to be true if C is independent of D given A. And let's look here to see if this is true or not. C is independent of D given A. So we are saying that C is independent of D given A. And that's not true because we did not observe B. So notice that the correct independence assumption that we have in this Bayesian network here is that C is independent of D given A and B, right? So it's important that we should observe A and B in order to block the influence between C and D. So we may ask, well, what kind of issues we may have when we use a joint graph instead of a joint tree. And we can compare the joint graph and the joint tree. So we have a joint tree for this Bayesian network that we had in the previous slide. It was ABC and ABD. And we have a larger cluster here, A, B, C, and D. And you have another cluster here, C, D, E. And we have these separators here, ABC and ABD. And here we have CG. So when we have those separators, what will the separators influence in this joint tree is the fact that when we send the messages over those marginals here, remember that the marginals are over the separators, we force the clusters to agree over the separators. So these two clusters, this one and this one, will agree over ABC, and this cluster here and this cluster here are going to agree over ABD. Indirectly, they will also agree over AB, because we have the message here that will include AB, and we have the message that comes back here and will enforce that these two clusters, so this cluster here and this cluster here, will agree over AB. But we do not have this guarantee anymore for the joint graph, right? Because we are not sending AB here and we are not sending AB here. So there is a risk that this cluster and this cluster, they will disagree over A and B. And in this case, we may have issues to compute queries that involve this marginal A and B. Okay, I think that is enough for this video. Let's take a break, and I'm going to continue in the next one when I'm going to formalize the iterative join graph propagation algorithm. See you soon.